Hi. In this video, I would like to show you how to model the flow in a two-dimensional unsaturated system or in a two-dimensional soil media using open hydroqual. Um, this specifically, I would like to actually, show you. I mean, first of all, how to create the model, but then also how to impose different kind of boundary conditions that are available in open hydroqual. The system that I want to model is actually quite simple, maybe superficial system. It's a two-dimensional vertical soil medium with a depth of 1.2 meters. I'm gonna assume that the groundwater table is at 1.2 meters below the surface, where I will impose a fixed head boundary condition. And then I basically assume, just to make the problem more interesting, I'm going to assume that half of the surface is covered with impervious area. So basically, water cannot infiltrate through this part. But then I'm going to apply precipitation to the other half. I'm going to assume that the surface has a slope of 1%. The dimensions of the domain that I'm going to model is actually, it has a 3 meters length. As I said, the depth to groundwater is 1.2 meters, so I'm going to actually model 1.2 meters of vadose zone. And then I'm going to assume that the width of the media, the block, is actually 1 meter. So you can assume that this is, we have symmetry or uniformity along the axis perpendicular to the page, and then all I have to do is to model 1 meter width. So basically what I'm going to do is that I will discretize this domain into 4 columns and 3 rows, and then I'm going to play with some boundary conditions on the right hand side. So let's get started. So I'm going to go to open hydroqual, and the first thing I'm going to do is that I will add a unsaturated soil plugin. So I'm going to go to preferences, add plugin, and I will add the unsaturated soil plugin right here. So this gives me some soil components. What I'm going to do is that I'm going to use the grid feature of open hydroqual so that I don't have to drag and drop every single soil block. So I'm going to create a 3x4 grid as we decided basically to discretize our domain with. So basically I'm going to go to add objects and then I'm going to go to create a 2D array. So here I need to indicate the blocks that will be used in the grid, and also the link type. Now, just to let you know, we have 2 link types for soil-to-soil connectors. We have a horizontal soil-to-soil connector, and we have a vertical soil-to-soil connector. The difference between them is that for the vertical soil-to-soil connector, we don't need to provide an interface area. The interface area is basically is taken from the bottom area of the 2 soil blocks that are connected to each other. For the horizontal soil-to-soil connector, the program will allow us to provide an interface area. And but then other than that, they're completely the same. The governing equations that are used are exactly identical. And basically, this array tool does not allow me to indicate 2 different link types for horizontal and vertical connectors, so I have to use one. So I'm going to go with just to make things easy, I'm going to go with the horizontal soil-to-soil connector, and then I'll indicate the interface area. So what I'm going to do is so basically I'm going to have, in horizontal direction, I'm going to have 4 blocks. In vertical direction, I'm going to have 3 blocks. And that's it. And then I'm going to go to next, where I need to provide the properties. So basically, I'm going to assume that the saturated hydraulic conductivity of soil is, let's say, I didn't provide that in my diagram, but I'm going to assume that it's 0.5 meters per day. There are some parameters that I don't have to be worried about in this example. The Wangenecton alpha parameter, I'm just going to leave it the default 1 per meter. And then an anisotropy ratio, I'm going to assume is 1. The bottom area of each soil block is going to be, actually let's go back to our diagram. So it's going to be, the width is 1 meter. The length of each of these soil blocks will be 0.75 meters because the total length is 3 meters and I have 4 columns, so it's going to be 0.75. So I'll have an area, a bottom area of 0.75 square meters. So let's go back to our model and indicate this to be 0.75. The bottom elevation of the soil block. So what I'm going to assume is that I'm going to assume this ground surface in the midpoint, actually right here, will have a bottom elevation of 0. Actually, a surface elevation of 0. So I'm going to assume that surface elevation here is 0. And then I will do some calculations of the bottom elevation. So basically, actually, yeah. So the next property that I need to indicate is the bottom elevation of the soil block. So this is how I do this. Basically, what I'm going to do is that I will assume that this point right here, the surface elevation at the center of the block is going to be my 0, my datum. So now what I need to provide in the box is the bottom elevation of my first block, which is this one, right? So I need to calculate what's the surface elevation at this point, the midpoint of my first block, and then go down 0.4 meters because each of these blocks heights is actually 0.04 meters. So basically this is what I'm going to calculate. I'm going to calculate this distance from here to here, and then I'm going to multiply that by my slope, which is 0.001, and that's going to be the elevation at this point, and I'll go down by 0.4 meters. Now this distance is going to be 0.75 plus 0.75 divided by 2, which is 0.0375. So here's how I calculate this. So basically, let me go to my calculator, and I'm going to type something, 0.75 plus 0.375 times 0.01, and this gives me this number. So this elevation is going to be the elevation of the center of the surface of the midpoint of my first block, and then I'm going to go down by 0.4 meters. So I'm going to get 0.038875. Let me just copy this and I will put it back here. Okay, then what I know is that when I move in x direction, the elevation drops by, basically due to the slope, the elevation drops. So here what this is horizontal increment. So as I move in x direction, how much the elevation drops. And what I know is, because the length of each of these blocks is 0.75 and my slope is 0.01, the value that the elevation drops is going to be 0.01 times 0.75, which is going to be minus, because it goes down, 0.0075. And then when I move in y direction, the bottom elevation actually drops by 0.4. So I'm going to put a 0.4 right here. The depth of each soil block is 0.4. That's pretty clear. I'm going to keep the default Wangenecton parameters because that's not the point of this example. So I'm going to keep the Wangenecton n parameter to be 1.41. I'm going to adopt the name soil. And then I'm going to keep the rest of the parameters the same. So initial moisture content, I'm going to assume is 0.2. Residual moisture content is 0.05. The saturated moisture content is 0.4. Now, one thing I'm going to do is, just to make the graphics that will be created a little more appealing, what I'm going to do is that I'll say the y is going to go slightly down, but then down in computer coordinate system is actually positive. So I'm going to say every block, when I move in horizontal direction, let's make every block to be on below the previous block by a value of, let's say, I don't know, 30. I'm not sure even that's going to be visible. So that's what I have. Then so that's it. That's all the parameters that I give to the blocks. Now it's time to provide the parameters for the links. So the first tab here, actually the third tab, is going to be link properties in x direction, right? So the interface area between these horizontal links, actually we're talking about these interfaces, this interface, this interface. So it's going to be 0.4, which is the height of each block, times 1 meter. So that's going to be 0.4. So let me go back here, and this is going to be 0.4 square meters. And the length is going to be 0.75, because that's the center to center distance between the blocks. So that's what I have. And then I go to next. The link properties in y direction, the interface area is going to be, basically now we are talking about this interface area right here. So the area is going to be 0.75, and the length is going to be 0.4, right? So basically this is going to be 0.75 and the length is going to be 0.4. And there's no increment. So let's just generate this. So here's what we got. We got our soil medium. Now let's start imposing the boundary conditions. So what I'm going to do is that I will just use a single fixed head boundary at the bottom. Now we can actually use 4 different boundary conditions at the bottom if it's necessary, but I'm going to keep that simple, and then I'm just going to use one fixed set boundary at the bottom, and then I will use the fixed set that I will impose is going to be equal to the bottom elevation of my lowest basically blocks. So basically I'm going to just put this fixed head. If I look at basically this block, the bottom elevation is minus 1.19, and then this one is going to be minus 1.2. So basically the midpoint between them is going to have a bottom elevation or elevation of minus 1.2. So that's what I'm going to put for my head. So I'm going to make this minus 1.2 meters. So that's going to be the fixed head. It's going to represent my basically groundwater table. And then what I have to do is basically there's this connector. It's a soil to fixed head connector. It's a vertical one. So I'm going to use this one, and I'll connect all these soil blocks at the bottom. I need to keep on clicking on this to my fixed head boundary. So that one, this one, and then this one. Okay, so that takes care of my bottom boundary condition. In order to receive precipitation, I need to basically have catchments. So I'm going to actually create 2 catchments up here, one above this soil layer and one above this one. And then I will not add any catchments above the soil 3.1 and soil 4.1 because I'm assuming no precipitation enters the soil through these. So so let me add the catchment. So I have one catchment, and what I'm going to do is that I'll just provide the parameters for this one, and then I'm going to copy paste. So basically now I need to provide a Manning roughness coefficient. Let's just, it doesn't really matter. I'm going to use 0.01. The catchment slope we know is 0.01. The width of the catchment is 1. The catchment area is 0.75. It's actually 0.75 meters by 1 width. And then I'm going to leave the depression storage at 0. The average water depth, that's initial water depth, is going to be 0. The mean elevation is going to be this number plus 0.4. Okay, so let's calculate that. Actually, we already know that number. it's already in my, so basically the number that I'm talking about is 0.01125. That's the center point of the surface, so it's going to be 0.01125. So let's enter that. I'm just gonna, yeah, 0.01125. So let's do that, 0.01125. No inflow, and that's basically it. That's all the parameters that I need. Now what I'm going to do is I will just make a copy of this, and then I'm going to paste it, and then all I have to do is go down by 0.75. So let me calculate this. Actually 0.0075. So basically the bottom elevation of this will be this number minus 0.75 times my slope, right, which is going to give me this number, 0.00375. So I'm going to go here and change this to 0.0075 meters, and then all I have to do is I'm going to actually connect one catchment to the other one here, and then I will also need to connect these catchments to the soil so that infiltration can occur. And for that purpose, I'm going to use this link. It's surface water to soil connector, right there. So this is the link that I'm going to use, surface water to soil connector. Let me connect this, and then I'm going to use another one for this. Okay. So now actually the only thing left is my right hand side boundary. So I'm going to impose some right hand side boundary, but by upstream I'm going to assume no flow comes in. So basically I don't need to connect this from upstream to anything else because no water comes in or go out, right? So okay, so basically here's what I'm going to do. I'm going to use a single fixed head boundary for my right hand side. Actually I'm going to do basically show you two options. We can have two types of boundary conditions at the downstream. One boundary condition that may apply to some problems is a fixed head boundary. So for some reason I know what's the head at my downstream boundary, right? It may cause some problems in some situations, and I'm going to show you how. But I'm going to first try that one, and then I'm going to change it to something that may be more appropriate for most problems that we deal with. So let me just add the okay, so I'm going to use the fixed head object by clicking on this here, the fixed head icon right here, and I add my fixed head boundary for my right hand side as my right hand side boundary. So that's what I have. Now for this one I need to indicate a head, a hydraulic head. What I'm going to do is that I'm just going to assume a head. If the head is actually high, what happens is that I'll have backflow, so water will actually flow from the fixed head to my soil medium. I'm just going to use a -1, a value of -1. Okay, so this is going to be the head of my fixed head. Now for connecting my, I need to connect these three soil blocks on the right hand side to my fixed head boundary. So what I'm going to use is that I will use this horizontal soil to fixed head connector. So I'm going to select this icon, and then I'm going to connect each of them to my fixed head. So then the last one, so this one too. Now I need to provide some information, some properties for these, these links. So one is actually the interface area. So the interface area, I'm going to assume that this interface area is the same as this interface area, which we applied a 0.4. So it's going to be 0.4. For the length, so it's actually length, centroid to centroid length. I'm going to assume that the length is half of the length of my soil block, which is going to be 0.375. So basically this is going to be 0.375. And then I have this other property, this property called outlet head. So what that is the way this link works is basically it uses the maximum between the value that I provide in my outlet head and the head of my fixed head. So if I leave the value at 0, then it will assume that the head of the end point of this link is 0 meters, which is above, most of my or all of my domain. So I'm gonna have backflow. One way to do that is actually I can provide a big negative number, and then this value will be used. I can actually also use different values for these different these three links too. So as I go down, I can use a lower value. For this case, what I'm going to do is that I'll just assign a negative number so that I make sure that this head is going to be used. And then, of course, you guys can play with it, use different numbers and see what the results is going to be. So let me do the same thing for here. So I'm going to say the interface area is actually 0.4. The length is 0.375. And the outlet head is, I'm going to assign -2, so that the head that I assigned to this fixed head will be used because it's a larger number. And the same thing here, let's say 0.4. The length is going to be 0.375, and then the outlet head is going to be -2. Okay, so my model is complete. Okay, now one thing that I need to do is that I need to I'm gonna assign some precipitation to these catchments so that I have some inflow water. So in order to add precipitation, I'm going to use this precipitation icon here. So I'm going to add the precipitation. The precipitation object will be added under my sources in the object browser. And this is my precipitation object. And I have a precipitation data file. I'll provide this in the link. But my precipitation data file is in this folder, climate data, and then sampled rain data. Okay. Let's look at the precipitation. So I can actually right click on the file name and then plot it, and you can see that I have a precipitation record from January 1st 2010 to the end of 2013, right? So but for my simulation, I'm just going to use 1 year of this. All right, so basically next thing, I will go to my settings, general settings, and then actually it's already set. So basically I'm going to say the simulation end time to be January 1st 2011, then simulation start time is going to be January 1st 2010. Okay, so so with that, I think and then one more thing, I need to apply the precipitation to the catchment. So I'm going to click on each of the catchments, and then there is this property called precipitation time series, and all I have to do is to select this precipitation object called precipitation 1 to both of them. Okay, so that's what we have. So I'm going to save my model, and then it's ready to be executed. So I'm going to actually run the model. It's going to take, less than 1 minute. Okay, saving the outputs. It's going to take a few seconds too. And we're done. Okay, so I'm going to close this. Let's inspect some of the results. So basically, I can look at the infiltration. So how much infiltration is happening. So let's just right click on this link connecting the catchment to the soil. And then I can go to flow, and you'll see this is how much infiltration is happening during the simulation time. I can look at whether there's any runoff. My hydraulic conductivity is quite high, so I don't expect a lot of runoff. But so we have runoff in one case. You had a little bit of runoff going from one catchment to another one. And I don't know, you can also look at the recharge, for example, how much flow goes from the bottom soil layer to the groundwater. So that's what you see. You see a negative value. The negative value is due to basically it's initially our soil moisture was quite low. So we have a high matrix potential in the soil, and therefore we had a little bit of upflow from the groundwater up. But then this is the recharge. I'm particularly interested in the flows into my fixed set boundary. So let's look at them. So basically, if we look at flow here, what you have is basically, as you see, we have a negative flow going on, and for the most part, we have a negative flow. So the reason for that is, if I look at the hydraulic head here, you see the hydraulic head for my soil 4.1 is minus 1.1, something around that. Okay, so that's below the head that I assigned to my fixed head, which was -1 actually. Slightly less. So that's what we have. We have this negative flow. If I look at this one, still have a small negative flow going in. So we have the water is not leaving our domain, is actually coming from the boundary condition into our domain. I mean, I can change that by lowering this probably, but anyways, if I lower this number, probably I'm gonna get flow going out. But then the problem is that our the model results will depend on the value of the fixed set boundary that we assign here. In some cases we may know that head, but in some cases we may not know it. So that's basically now I'm going to talk about another approach to avoid that problem, to make sure that the water actually leaves our domain. So in order to do that, what I'm going to do is that I will use this basically link called fixed hydraulic gradient. So what I'm going to do is that instead of providing a fixed head, I'm going to provide a fixed hydraulic gradient here, and that hydraulic gradient controls how much water leaves our domain. So what I'm going to do is that I will delete these links and I will replace them by a fixed hydraulic gradient link. Okay, so I'm going to use this fixed hydraulic gradient boundary condition. It's marked by partial h over partial n, and I'm going to connect my 3 soil blocks on the right side to my fixed head boundary. So here you go. And so now I need to assign some properties to this. So the properties are, one is hydraulic gradient. So what I'm going to use for hydraulic gradient, I'm going to use the slope of the surface. So that's the most reasonable assumption. Essentially what it says is basically it's at the boundary, the soil blocks are behaving similarly to the imaginary blocks that are not inside my model, but they serve as my boundary. So what I'm going to do is I'll just assign this 0.01, which is my slope. I also need to provide an interface area, which I'm going to use the same interface area as between these two soil blocks, 3141 for example. So that's going to be 0.4, and I'm going to do the same thing for the other boundary conditions as well. So the hydraulic gradient is going to be 0.01. The interface area is going to be 0.4, and same thing here, 0.01 and then 0.4. Okay, so let me save my model and I'm going to get another run. So let's just run it. Okay, so saving the outputs and done. Okay, so now let's inspect our results. So basically I'm going to look at the flow here, going through this link. So if I look at the flow, I get a positive number right there. Now you may ask, what's the reason for the fluctuation? Why do we have, a time variation? Because our hydraulic gradient is fixed, but keep in mind that the effective hydraulic conductivity is calculated based on the moisture content in the right hand soil blocks, and the effective hydraulic conductivity depends on the effective moisture, which is time variable. So that's why we have this time variability here. I can look at the other links as well, and I'll see that the water actually leaves our system according to the provided actually here provided hydraulic gradient. Okay, here you go. Okay, and this was all I had for this video, and thank you for watching.